Welcome, focus learners, to this explainer. Today, we're unpacking the fascinating engineering that's shifting artificial intelligence from massive, power-hungry data centers right into the palm of your hand. It's literally a revolution in optimization. Okay, let's dive into the central mystery here. How do you actually fit a trillion-parameter AI in your pocket? Because look, as the industry moves from experimental foundation models into widespread production, the sheer physical and economic costs of that massive scale are hitting a brick wall. Here is how we're going to break this down today. We'll start with the AI size problem, move into the model compression toolkit, look at Google's efficiency breakthroughs, explore compressing during training, and finally, look at the edge AI revolution. Let's jump right into section 1, the AI size problem. We've got to start with the core issue. Foundation models have billions of parameters, right? And they require gigabytes of storage, plus highly specialized, power-hungry hardware. So the crucial point is that this kind of operational overhead is just completely unsustainable for everyday use. It creates this massive tug-of-war between computational efficiency on one side and model faithfulness, which is basically how accurately a compressed model mimics its massive, uncompressed predecessor on the other. To solve this, developers use a really specific set of methods. Welcome to Section 2, the Model Compression Toolkit. This brilliantly illustrates our main toolkit. It gives us a mental map of 4 core strategies we can use to structurally or numerically lean out these massive networks. They all target different parts of the neural network lifecycle, drastically reducing the memory footprint without totally wrecking core performance. Let's look at our first archetype, quantization. Think of it kind of like lowering the resolution of a highly detailed photo. By shifting from standard 32-bit floating points down to 8-bit integers, the model instantly takes up 4 times less space. And because neural networks are naturally pretty robust to noise, this coarser resolution still leaves the model entirely functional while unlocking massive speedups on modern processors.
Now, what's really fascinating is how developers actually apply this numerical reduction. They can go with post-training quantization, which is exactly what it sounds like, a quick, simple compression after the model is built. Or for a more rigorous approach, they use quantization-aware training that simulates the rounding noise directly during the training process itself, which lets them network adapt and achieve much better accuracy even at ultra-low bit widths.
Next up, we have structural sparsity. Pruning is literally just like trimming dead branches off a tree to make it structurally sparse by cutting out non-essential parameters. And when you combine that with machine learning-driven neural architecture search, the results are wild. This specific combo famously allowed Google's EfficientNet to match the accuracy of the standard Resonant 50 model, but at literally 1/5 the physical size. Let's move over to knowledge distillation. This is essentially a master craftsman passing down secrets to an apprentice. The large, complex teacher model generates what are called soft targets, which are these rich probability distributions that reveal its internal reasoning. Then, a smaller student model learns to mimic that behavior. This technique famously let Distilbert retain 97% of the original model's performance while being 40% smaller and a whopping 60% faster. This brings us to Section 3, Google's efficiency breakthroughs. To really wrap our heads around extreme engineering breakthroughs like Google's TurboQuant, we first need to define the key value cache. Large language models use this cache as a sort of memory bank to remember conversation history and keep things coherent. But as the context window grows, this cache expands linearly. It just eats up available GPU memory until the whole system crashes. Enter TurboQuant. It solves this efficiency tax using a crazy 2-stage mathematical process. First, PolarQuant applies a geometric rotation to transform messy, irregular data into a predictable shape on a circular grid. Then it uses quantized Johnson-Lindenstrass, try saying that 3 times fast, or QJL. QJL acts as a 1-bit mathematical error checker to eliminate bias and attention scores. That ensures the compressed version stays statistically identical to the original. The math there is super heavy, but the result is absolutely incredible. By managing the data shape and checking the errors, TurboQuant gets a 6x reduction in memory usage for the key value cache, with virtually 0 accuracy loss. And as if that wasn't enough, its 4-bit implementation gets a massive 8x performance boost when computing attention logs on NVIDIA H100 accelerators. That means context limits can nearly double on the exact same hardware, making long-form content generation incredibly cost-effective.
Google is also pushing to bring AI natively to your phone with Gemini Nano. It uses a hybrid strategy called quantized distillation to run models entirely locally. This gives you 3 huge benefits. It keeps your private data secure because it literally never leaves the device. It completely eliminates remote server latency so you get real-time responses, and it saves your battery life. A real win-win-win.
All right, let's look at the next frontier in Section 4, compressing it during the training.
Okay, so what if we didn't have to wait until a model was fully baked to start shrinking it? Researchers over at MIT and Google developed Compress SMM. This technique surgically removes unnecessary components from state space models while they are training. It basically figures out what isn't pulling its weight early on, maintaining near full accuracy while actually speeding up the training time by up to 1.5 times. Then you have advanced parameter sharing methods like COLA and SLTrain, which are fundamentally rethinking how knowledge is stored right from inception. By bringing low-rank concepts directly into the pre-training phase itself, these methods cut the required computational operations in half without losing performance compared to their massive uncompressed counterparts.
Finally, let's tie this all together and look at why it actually matters to you in Section 5, the Edge AI revolution. Model compression is the key that unlocks Edge AI. It moves processing directly to the source of the data, which enables massive real-world returns without constantly relying on the cloud. For instance, in manufacturing, local predictive maintenance is slashing downtime by 67%. In healthcare, edge-powered systems like BioBeat provide continuous vital tracking even if the internet goes down. Retailers are using on-device YOLO vision models to instantly manage checkout queues. And telecom cell towers, they can dynamically adjust bandwidth on the fly. The ultimate takeaway from all this is democratization. The barrier to entry is dropping fast. Thanks to these wild compression techniques, smaller teams and scrappy startups can deploy advanced, highly efficient AI to actually challenge the tech giants. The secret sauce of AI is no longer just having the biggest data center, it's the elegance of your optimization. We've seen how reducing precision, trimming dead weight, and leveraging advanced math can put unbelievable power right into our pockets. Which leaves us with one final thought to chew on. If AI's true power increasingly lies in its absolute smallest forms, what will you build at the edge?